right. Well, I guess I'll get started. I know a lot of people watch the recording. So, John, if you have to leave at any point, or if anyone else joins on, y'all say the same thing, don't feel bad at all. I have to be here for an hour anyways, so I will do this. I'll post the recording on YouTube as I normally do either today or tomorrow. And then after that, if you have any questions or if anyone watching this later on has any questions, just let me know, and I'd be happy to meet another time and we'll go from there. But all right, so this week is week 3, and this week definitely is challenging, a lot more challenging than the other weeks. So I hope that this PowerPoint is of use. And I'll probably do a couple examples at the end too, just because I think that this week, more than any week, is where people have issues. So let me share my screen and we'll go from there. So let's see. Sorry, let's make this bigger. Perfect. Okay. So you should be able to see my screen right now. So again, this is week 3. So a quick recap on last week. So we talked about series circuits and how to calculate equivalent resistance. So this week we're going to be doing the same exact thing, but now we're going to be talking about parallel circuits, and it's a lot more complicated of a procedure. As you can see that equation there, 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3, etc. It's a lot more complicated to deal with. On top of that, there's a few other elements kind of brought into this week that make it a little bit challenging. So hopefully not too bad, but we'll work through it. So, all right, so just a little bit more on parallel to talk about. These are just some points that are really, really important. When talking about branches, we're talking about the areas right here, like these lines, like this is a branch, this is a branch. Obviously, in something like a series, you don't have any branches because it's just one, or you can have branches, I guess, but they're more important in a parallel series because of, or a parallel circuit because of, like calculations we make. So these are what it's referring to when it says branches. So like, every branch in this situation has a resistor in it. And typically for the models we're going to get in class, I know in later weeks, a few people have turned in the homework assignment that is one of the ones we have to write in person. It talks about how it has 2 branches, and you kind of just have to make the interpretation that there's a branch on, or that there's a resistor on each branch. So this is kind of something you can, unless they tell you otherwise, I would just kind of assume that however many branches there are, that's how many resistors there are too. So, so basically, the other important thing here is, so all of those branches, so again, like these pathways, again, these branches are just pathways that are current or electrons, because again, electrons flowing through a circuit is what current is. All of these different branches might have different currents or resistances depending on the resistors, and the resistors are basically how what impacts current. And we know that by our Ohm's law, that current and resistance are related, and impacting or increasing or decreasing one of them is going to increase and decrease the other. So basically that's really important for this. Make sure you understand that, so that branches within one parallel circuit might have different currents or resistances depending on the resistors. And we'll talk a little bit about we'll talk a little bit more at the end about how that's calculated. So basically what that means is that, like this line right here, the electrons flowing in this line might only be going 2 amps. The electrons that don't take that pathway and go this way instead might be going 1 amp. And we'll talk about how you calculate that. So the other important thing here is, let's say that we have a circuit that has a 10-volt battery. That means that the voltage of each branch will be, this should be 10. So that's the only thing there too, is that your voltage is, like whatever you start with, your initial voltage and your final voltage is always the same. So that's important to note too. So really the only thing that we're calculating is our current and resistance at a given point in time, because those are the 2 things that change. Okay, So now we're going to do a little example about how to use this equation. This one right here, because again, this is how you're calculating the equivalent resistance or the total resistance of a circuit. So this is how I would recommend doing it. So as you can see, this is the same equation there. It looks a little bit different than this equation. So as you can see, this equation right here is different than this equation. It is the same one. This REQ is our RT, so it's the same value. This is just saying resistance, total resistance, and this is saying equivalent resistance, same thing. But they just basically use math to get rid of this one on top. So we just have RT. So I would go at, I would use this equation. That's the easiest equation to remember. So basically, in order to calculate total resistance, you find these fractions and then do 1 divided by the sum of all of those. So this is basically an example, and I can do more if more is needed. So let's say we have a parallel circuit with 3 branches. Okay, we're just gonna say 3 right here, 1, 2, 3. This example right here is showing that you might have multiple branches or multiple resistances. So you could have 10, but we're just looking at, basically you can say it cuts off right here. We're just looking at this R1, R2, R3. So we have one with 3 branches and 3 resistors, all with 50 ohms. So each resistor equals 50 ohms. Find the total resistance. So all you have to do is this exact equation. So first, I would write down everything you know and try to be as organized as possible, because if not, it's easy to make mistakes. So we know R1 equals 50, R2 equals 50, R3 equals 50, all of that, because it shows us right here that all of those 3 branches have 50 ohms. So then, as this bottom equation shows you, you do 1 divided by all of those resistor values. So 1 divided by 50 is 0.02. So that's 1 over R1, right? Because 1 over R1 is 1 over 50, so it's 0.02. But since we know R2 is 50 and R3 is 50, that means that 1 over R2 and R3 are the same thing as 1 over R1, which is 0.02. This equation then tells you to add all those together. So you do 0.02 plus 0.02 plus 0.02, which is 0.06. So this bottom half of the equation right here is done. We know that 1 plus R1 plus 1 plus R2 plus 1 plus R3 is 0.06. And then it tells you to do 1 divided by that number. So 1 divided by 0.06 is 16.667. So this right here is the total resistance. Let's highlight that because it's important. So again, just kind of work through it, make sure that that's totally set in stone. In order to calculate the total resistance, you need to know the ohms of which is the unit for resistance of all of the resistors in your circuit, because not every whatever one resistor is does not mean that's what your total resistance is. So in order to calculate total resistance for a parallel circuit, you're going to use this equation, which is the same thing here. They just use math to figure out this equation to get RT by itself, which is the easiest way to do it. So I'm going to probably do a couple more examples of this exact problem to kind of show the math behind it and make sure that everyone understands the math behind it. Okay.
Yes. Great.
So, hi. So this slide is really, really long and looks really complicated, but I'm going to run through it because this has the gist of the information for this week. So this slide alone is enough to almost get half of the questions. If you understand this slide, you will understand the majority of this week. And I think that the questions, like if you take the quiz or if you haven't taken the quiz, so if the people watching this referring to, if you haven't taken the quiz yet, make sure that you understand this concept completely, because if not, it can be really, really challenging. So basically, I think the best way to do it is an example. So again, we're using this equation up here, this 1 over REQ, which is just RT equals 1 over R1 plus 1 over R2 plus 1 over R3. But that is the same thing as using this equation right here, RT equals 1 over. All they did here in this equation and this equation is they use algebra rules to get rid of this 1 over RT, so it went on this side, so it's easier to solve. So let's delete this one because I would memorize when solving the total resistance for a parallel circuit, I would definitely use this equation. Okay, so let's say we have an example like this, where we have a parallel circuit with 20-volt battery, 2 branches, one with 20 ohm and one with 10 ohms. What will be the current on the 20 ohm branch, the 10 ohm branch, and the total current? So this is going exactly back to what we talked about here. So in a situation where you have a lot of resistors, no matter how many you have, that means that your current at every single branch, wherever your resistors are, won't always be the same. So your current and resistance at a given point in time in your circuit might change. Your voltage, on the other hand, whatever you start with and whatever you end with, your voltage never changes, but your current does change. But same with that, I guess, principle, current and resistance always at the end will be the same. So whatever speed is coming out right here, however fast those electrons are going right here, is however fast they're going right here. But in this line, and this line, and this line, and this line, it's not always the same. So that's what we're calculating in this problem. So it's the fact that we need to calculate the total current, the current at one particular branch and another particular branch, because they're not all the same. And I'll kind of show you, hopefully with this, what that means. So the first thing to start with is these first 2 questions it asks. So in order to calculate the current at just one branch, you can kind of treat it like how we did the first week of class, where we just used that simple equation right here, Ohm's law, I equals V over R. So basically, if we looked at this picture right here, that first question, what would be the current in the 20 ohm branch? I would pretend that we're only looking at this first little, like at one, we're only looking at one thing. So pretend we just have one resistor in a circuit. So all you have to do is use that same equation. So it's I equals V over R. And we know that the battery is 20 volts because voltage, as it says right here, voltage never changes. And we know the resistance is 20 ohms because it says it right here. And you can just do it as simply as I equals V over R, which is 20 over 20, which is just 1A. It should be 20 over 20. So again, all I did here was, in order to calculate the current at a given branch, all you have to do is use Ohm's law, I equals VR. There's no having to use this equation, and that's solely because it never asks for the total current. It's only asking for the current at one particular area. If it asks for the current of the whole entire circuit, that would be the total current. But in this question right here, just the 20 ohm branch. So that's why, no, we don't have to do any of this. It's the same thing for the second question here, the 10 ohm branch. You follow the same exact rules. So we know the equation I equals VR. Our voltage is 20 because voltage never changes throughout your whole circuit. But this time our resistance at R2 is 10 ohms. So we do 20 divided by 10 to get an I of 2, or a current of 2. The last little bit, this is when it gets everything comes together. It's where this question we did comes together, and it's where understanding Ohm's law comes together. So if we have to calculate the total current, you have to know your total resistance. So if it ever says find the total current, or if it ever says find the current in a parallel circuit. So if it just says find the current in the whole circuit, like it doesn't say find the current at this location. If it just gives you a specific or a broad question that just says find the current in this parallel circuit, this is when you have to first find the total resistance. And the total resistance is found using this equation. Similar to how last week we used this equation, which was just the sum to find the total resistance of a series circuit. Now we have to use this equation because parallel is just a little bit more complicated because of how they work. So basically, I'm not going to do the calculations here because I already did them here, or here to show you an example, but I'll do more if more is needed. But the way that I calculated total resistance was I would have just done RT equals 1 divided by 1 over 20 plus 1 over 10. And that would have given me the 6.66. And then since I know my total resistance, I can use the same equation, I equals VR. Right here, I equals V over R, which is just 20, which is our total voltage, and then divided by 6.66 now because that's our total resistance to get 3 amps. So I wrote it out here too, just so everyone like the quick math about it. So what I did to find our total resistance was same thing I did for that problem I showed at the beginning. You use this equation and you do 1 divided by the sum of the fractions of all of your resistors. So I did 1 right here divided by 1 divided by R1, which is 0.05, and 1 divided by R2, which is 0.1. And then I did 1 divided by the sum of 0.05 plus 0.1 to get 6.66. If you do the math, it'll show you that too. So that's basically what you're going to be asked in this week. So you're going to be asked to know how to calculate the current at a given point in time in the circuit. So at a specific branch given a resistor, or you're going to have to find the total current. And in finding the total current, you have to know that right there, the total resistance. So you have to know how to use this equation. Once you use this equation, then you can just use Ohm's law. So no matter what, if you're asked to find the current, the resistance, or the voltage, at the end of the day, you're going to be using I equals V over R. However, when we're calculating our total current and not just the current at a given point in time, that's when we have to take that additional step of doing this right here. And some problems you have to, this is when you kind of have to be careful with the wording, because some problems might already give you that total resistance. If they say in a problem, the total resistance is 6.66, you know, they might give you this total resistance in the problem, then you know, okay, that's the total resistance. So in order to calculate the total current, I don't have to do this step. I just have to do the Ohm's law, which is just the I equals V over R. So this is why, like, reading the questions carefully and understanding the fundamentals for when you have to use this equation, when you don't, understanding the concept of, you know, I might have 2 branches with a resistor on both, one branch with a 20 ohm resistor and another branch with a 10 ohm resistor. So understanding that concept too is really, really important. But like I said, this is the main thing. If you understand this, the rest of it's a breeze. And the most challenging portion is probably using this equation. So definitely do practice with that. For me, I think it's easy to make mistakes when you're typing things in a calculator. If you don't have parentheses where they should be, it's not going to do the division right. So how I would do it is first, kind of like how I did this problem first, write in like a notebook, okay, R1 equals this, R2 equals this, R3 equals this, and then do this portion of it. So do the easy fractions first. So once you get whatever that equals, like in this 1 over R1 equals 0.02, sum those all together, and then whatever that number is, when you add them all together, do 1 divided by that number. Because if you just in your calculator right now typed in 1 divided by 1 over 50 plus 1 over 50 plus 1 over 50, because this is it, your calculator is probably going to mess something up because you don't have, because it needs parentheses to understand like where that base of the numerator and denominator is. So basically that's how I would do it. First, calculate these fractions of all your resistors, and then add all those together, and then do 1 divided by that. So that's all I did in this last part 3 of this. But 1 and 2 were easier because I just needed the current in a specific place. So the main takeaways from this, just know that you can calculate current at every branch. And in order to calculate current at every branch, you don't need to know total current. You just need to know the resistance at that branch. So the resistor, whatever resistor value you have. And you can also calculate total current. So know how to calculate total current, know how to calculate current. And know that in order to calculate total current, or the current of the whole entire circuit, you will need to find the total resistance using this equation right here for a parallel circuit. Okay, so this is the same exact thing, but again, we're just going to show it again because it's important, and I want to make sure that the fundamentals here are given. So let's say we have a problem that's worded like this. We have a parallel circuit with 3 branches, 1 branch with 15, 1 branch with 25, and 1 branch with 100. There is a 25-volt power battery powering the circuit. What is the total current in this circuit? Okay, so first I'm going to highlight a couple things that are important to this. One, the fact that it says parallel. So we know that we might need this equation, right? Oh, you cannot see that. Very different color. That's still blinding. My goodness. That's fine. The other thing important here is that it says that we have 3 branches, each branch having one of these ohms. So that means that we have 3 resistors in this example. So R1, R2, R3. And then it says if we have a 25 volt battery. Okay, and we know the voltage never changes, so that's easy. And then the other thing important is that it says total current. So it's not asking for the current at a given branch, which we could do that. We know that if we needed the current at the 25 ohm branch, all we would have to do is that equation that we did for these problems, I equals VR. So we would just do V 25 divided by 25, and that means I equals 1. So it's as simple as that. But in this situation, since we need total current, we need to use this equation. So first, you need to calculate your total resistance, because in order to calculate total current, you need total resistance. So I would write it down. R1 equals 15, R2 equals 25, R3 equals 100, because this tells us that. Then we can use this equation. First, do your fractions. So if you did 1, I'm going to just do this on my phone. So 1 over R1, so 1 over 15, 0.0666. So you might get fractions, like that's totally fine. So 1 over R1 equals 0.06666. Now we can do 1 over R2, which we know would just be 1 over 25. And it doesn't matter if you call R1 25, R2 15, as long as you just call, as long as you take into account whatever ohms you're getting. So 1 over 25 is 0.04. You can do the math if you want to here to make sure I'm right. I sometimes mess it up. And then R3 is 1 over 100, which is just 0.01. So the next step here, this plus sign tells us to add all of those fractions together. So we're going to add over 1 plus over R1, which is 0.06, 1 over R2, which is 0.04, 1 over 100, which is 0.01. 0.01 plus 0.04 plus 0.0666 is 0.1166. So we know this bottom right here is 0.1661. I'm going to write this. That bottom portion there equals 0.1166. But now we have to do 1 divided by that, right? Because we added all these together, or we calculated all these fractions. Now we added them all together to get 0.1166. And now this equation tells us to do 1 divided by 0.1166, which, if you did the math, it is 8.57, which is what I had for RT. Now that we have RT, it's the easy stuff that we're totally used to, which is we just use this equation, I equals V over R. We know that the voltage is 25, it doesn't change. So you do 25 V divided by resistance, or total resistance, 8.57, to give us 2.917 as our current. So again, same situation. The only difference between this and the problem we did right at the beginning is each resistance had the same ohm value. In this situation, we had different ones. So you're going to follow the same steps here, depending on if you have 2 branches, 3 branches, 4 branches, 10 branches. It doesn't matter. It's the same step here. You do this part, find your fraction of each R1 or R2 and R3, etc. Add all those together, do 1 divided by that number, that's the total resistance, then you use this equation. Okay, so now we're going to talk about something, the last little bit that is important for this week. And this is a question that is on the the quiz for this week, and a lot of people I've noticed have gotten it wrong. So definitely pay attention to this portion. If you haven't paid attention to anything yet, I would pay attention to this. So if you understood everything we talked about, this is where everything kind of really show if you know and understand. So let's say that we have a junction with 2 branches. The word junction just means a point right here where it separates. So this is a junction because we have electrons. The electrons, let's say they start right here, they're going around here, then they stop. Some of them are going to go this way, and some of them are going to go this way. And that's the whole intent of a parallel circuit. We don't always have electrons going in the same path. There's multiple paths for them to take. So basically this is telling us that in order to calculate the speed or the current right here or right here, the current before a junction, which is 10 amps going into this junction, has to equal the current going out of a junction. So that means that this is, if we knew that this was 5 amps, we can automatically know that this is 5 amps. And that again is because the sum of the current leaving a junction has to equal the sum before. And this is why, because what I talked about right at the beginning, so even though our branches might have different currents, which is what's happening here, at the end of the day, the current, I'm going to add this because it's important, the current at the beginning and end of the circuit is always the same. And that's important for this last little bit here. Because right here, these electrons that took this path and these electrons that took this path here are meeting again at another junction. And that means that our current changes. But it's this time we're adding it again. So the 5 amps coming down here, the 5 amps that went like this and stopped here, these are going to meet together and speed up that flow of the electrons, and now they're going to go 10 amps again. So basically, what we started with and what we ended with were the same, but our current changed in the branches, and that's because at every junction, your speed is going to split up. And it might not always be equal like this, where one's 5 and one's 5. But let's look at this example that we just did. This is interesting. So in this situation, when we first calculated our 20 ohm, when we did the math, we got 1 amp. When we did the math on the second one, the 10 ohm, we got 2. 1 plus 2 equals 3. So the sum of those branches equaled the total current. And I think it would help if I drew this out. So I was going to use my iPad, but I think it might be difficult because I want you to still be able to see this problem. So I'm just going to draw it up here. So let's say let's draw this exact thing. So here's my circuit. And we had two, maybe that to just be, so in this situation, we had 2 branches. So we'll do, let's say we'll put a line here. Okay, so let's draw out what we know. We know this is my battery, which again is our power source. So we know that our battery is a 12-volt battery. So let's write that here. So that is the voltage that we're starting with. And then we know that we have 1 branch or 2 branches, one with a 20 ohm resistor. So let's draw a little bit like a resistor here. Maybe. Oh my goodness, maybe. Come on. There's no line. You know how they do that, like Z for the resistor? We're just going to pretend that this is our resistor. Oh my goodness, it does not need to have a line. You know what? I'm going to draw this because this is way too complicated. So, okay, first just remember this. I'm going to draw this on my iPad. It's going to be way easier. But just remember that we had 1 ohm with a 20 ohm, or 1 branch with a 20 ohm, and another branch with a 10 ohm, and that the 20 ohm was 1 amp, and the 10 ohm was 2. So, because the screen's going to go away in a minute, I think. Okay, so now I'm going to draw this. Hopefully, are you able to see that, right, what I'm drawing? Okay, perfect. So, as this problem stated, we had, again, and if you look back at it, it'll show this, we had a 20-volt battery to begin with. We had 2 branches, one with a 20 ohm, so we're going to have our resistor here and say that it's 20 ohm. And then we had another one with 10 ohm. So let's say that we had that here. And this is 10. And we know from our calculations that the voltage or that the current on the 20 ohm branch was 1 amp. So at the 20 ohm branch, we calculated that the current was 1 amp. At the 10 ohm branch, we calculated that the current was 2 amps. So that means right here, the current and the speed of the electrons that are going down this path right here are going 1 amp. So that's the speed. We know the electrons that are going this way are going 2 amps. And we know by the rule that I just talked about, once those electrons meet right here, right, because they're going to meet right here, the electrons going down this arrow, this 20 amp branch, and the electrons going this way are going to meet up right here, and then we sum those together, so 1 amp plus 2 amp to get 3 amp as our total current. So again, that's just showing the principle that if you have to calculate the current in a specific branch, like we had to do right here, if you know that, you can actually skip that whole long step of finding our total current, because you don't have to use that equation if you know this, because we just know that the sum of it is going to equal 3, and we know that that's what we started with. So what this is telling us too is that right here, this has to equal 3 amps, which makes sense because it means that once those electrons that were flowing here met at this point, they split up, some with the speed of 1 amp, some with the speed of 2 amps, and then when they met back up at this corner, now they're both going the same speed of 3 amps. So basically that's the same exact thing of what I did here. Ooh, that's already good. So it's the same exact thing of what is going on here. So in this situation, the electrons flowing right here stopped at this junction, and then the speed slowed down or split up, and some went 5 amps, and the other went 5 amps, and then right here, they met back up and went 10 amps. It's the same example of what I just did, where I used this whole scenario here. At that branch, we had some going 1 amp, so right here, we had some going 1 amps. Right here, we had some going 2 amps, and then they met back up and went 3 amps. So that's the main idea. Again, if that's confusing to you, if there's anything that I need to explain better, if I need to, meet with any of you again, if you're watching this recording, if there's anything at all that I can help with, let me know. I'd be happy to meet again. I'd be happy to do more examples until this is something that you understand and it's not something you have to stress about. So the last little bit, which is the easy portion of this week, is it talks a little bit about a multimeter. So hence the word multi, it means that it can basically measure multiple things. So a multimeter can measure volts, amps, or ohms. So it can measure volts, which is voltage, amps, which is current, or ohms, which is resistance. And this is basically applicable to like real world situations, which is why we talk about it. You might have seen one of those before. I'm certain that all of you majoring in electricity will, or any type of electrical applications, you will use this. So that's the main idea. Just know that it can be measured, or that it can measure multiple things, and that's volts, amps, and ohms. A few other points here to measure is, in order to measure resistance using a multimeter, you have to have your circuit turned off. So you have to turn off your circuit, and that's basically just to obtain an accurate reading. And there's not a lot like you have to understand behind that, but I think a lot of it just has to do with the fact that unless you turn it off, you might be getting it might be trying to read all the resistors, because obviously your total resistance might not be the same thing as like one resistor, right? Because we can have multiple resistors all with different resistances. So if you don't have it turned off, it just doesn't give you an accurate reading. So that's important too. So a voltmeter is basically just something that can measure the electrical potential difference between 2 points in an electric circuit. So just a voltmeter, volts. An ammeter is a measuring device used to measure electrical current. So we have a multimeter, which is obviously the best to use. Multimeter can measure all of it. A voltmeter can only measure voltage. Ammeter can only measure current, and then a voltmeter is connected in parallel with the device to measure its voltage. So that's just like a procedural thing to kind of recognize the difference of voltmeters and ammeters, besides the fact that they measure different things. So a voltmeter is connected in parallel with the device, and an ammeter is connected in series with the device to measure its current. So, and basically at the heart of most analog meters is a galvanometer. So it's basically an instrument that measures current flow, the movement or deflection of a needle. And the needle deflection has to do with magnetic forces and magnetic fields. You don't really have to know that. I just think it's interesting to know all the different types of meters you might be using when trying to measure different things. So main idea for when talking about a multimeter, just know that a multimeter can measure this, and know that the difference between a voltmeter and ammeter is that one measures volts, one measures currents, and that one has to be connected in parallel and one has to be connected in series, and that should be sufficient enough. But yeah, so that is basically all I have for this week. So I don't have anything else, but if you have any questions, again, you can ask them now. I can stay on. So if any of you have answers or questions, I can answer them. If you want me to do a few more examples, I can do that too. If not, you're free to head out. And if anyone watching this recording has questions, send me an email and I would be more than happy to help. So, but yeah, so I'm gonna close this out. And yeah, so that's all I have. Yeah, early, but I'll stay on if I don't know. You guys have any questions? Thanks, you too. Hi, Michelle. Hope you're doing all right. Do you have any questions at all? Or do you want me to?
Yeah, actually I do. Did you ever see if that what module was it? Hold on, let me find it.
Oh, your email? Is that what you're asking me about?
Yeah, that I did that module. I did the whole module. It took me like a freaking